So today we're going to be looking at what a logarithm does. First thing we'll do is try taking log of some random numbers. So for example, log of 7 is 0.845. Log of a million or billion is 9. And log of 16 is 1.2. Let's try some powers of 10, maybe 10 squared, 10 cubed, 10 to the power 4, and 10 to the power 5. See what happens when we take log of these numbers. Log of 100 is 2. Log of 1,000 is 3. Log of 10,000 is 4. And log of 100,000 is 5. So you can see that log kind of works as a zero counter. It's counting how many zeros there are. Well, what happens when we try numbers that are multiples of powers of 10? Like log of 20. It's 1.3. So this number has one zero, but it's a little bit bigger than 10. So it's not just 1, but 1.3. 400 is 2 zeros, but it's bigger than 100. So that's why we have the 0.6. 2 zeros, 0.6 is because 400 is a little bit bigger than 100. Log of 8,000 has 3 zeros, and it's almost at 10,000. So we have 3.9. And log of 160,000 is 5.2. Because there's 5 places after the 1. Well, let's see, if we take some numbers that have the same number of significant digits. All these numbers start with 2, 4, 3. Log of 2.43 is 0.385. If we multiply that number and move the decimal place over 4 places, then the log becomes 4 numbers bigger. That's just, we took this number, we moved the decimal over 1, 2, 3, 4 places, and the log became 4 more. If we move that decimal place over even further, then the log becomes even bigger, 6.3856. Try some roots. The log of a square root is a half. Log of root 0.1 is negative a half. And log of root 10,000 is 2, because the square root of 10,000 is actually 100. Now when we try to do log of 0, something interesting happens. Log of 0 has no answer. We could say does not exist. Same thing happens with negative numbers. Log of negative 1 is not real. Log of negative 2 is not real. So we can't take logs of negative numbers. So a log really gives the exponent in base 10 of a number. The best single word that describes a logarithm is that it's an exponent. And a common logarithm is in base 10. So when you see log of x, what it really means is log base 10 of x equals y. And this has the same meaning as 10 to the power of y equals x. So if you have a log on one side of an equation, you can take that log and move it to the other side of the equation by making it the base of an exponent. And it pushes everything else on that side of the equation up into the exponent, leaving the x on the left-hand side by itself. Logarithms can happen for any base, but we can't have negative bases, and we can't have a base of 1. Log base a of x equals y means that if you wanted to take that a to the other side, it would become the base of the y of the exponent. So that would mean a to the power of y equals x. So log base 2 of 16 equals 4 is just another way to say that 2 to the power of 4 is 16. A common base is base e, 2.7182818284659. It's an important irrational number. And if you want to write log base 2.718, we use this one so many times that we're going to write it as a special letter e. And we can also call that the natural logarithm, ln. So ln of x is the same thing as log base e of x. We won't be doing that one too much, but it's important for calculus. So when you see something like log base a of a, what this means is a to the power of what number equals a? That number is 1. A to the power of 1 is a. So this expression is just telling us, we took this part to the other side of the equation, it's just telling us that a to the power of 1 is the same as a. So same thing here. You take the base to the other side of the equation, it becomes the base of an exponent. So this expression is telling us that a to the power of 0 is 1. And the last one is saying that a to the power of x is the same as a to the power of x. So we can use this to determine some logarithms. Log of 400 is 2.6. If we rearrange that equation, that means that 400 is the same as 10 to the power of 2.6. So if we did 10 to the power of 2.6, we get pretty close to 400. Just need to keep all the decimals to get exactly there. Log of 0.35 is negative. And that means that 10 to the power of negative 0.444559 is about 0.35. So you need a negative exponent in order to get an answer that is less than 10. So we can check. 10 to the power of 0.449 is pretty close to 0.35. Log of a negative number has no answer. Because we move that log to the other side, 10 to the power of what number would give a negative number? If we tried 10 to the power of negative 1, the answer is a decimal. It doesn't become negative. There's no way that you can use an exponent to create a negative number. Log base 3 of 243 means 3 to the power of what number equals 243? I believe that answer is 5. 3 times 3 times 3 times 3, 5 times, is 243. So you need 5 powers of 3 in order to get 243. Log base 5 of 4 means 5 to the power of what number equals 4? That's a little harder to do, so we're going to use a change of base identity. And the change of base says this: if you take the log of your primary argument divided by the log of the base, and this is a way that you can change the base, because we have no way to write that little 5 on the calculator. So log of 4 divided by log of 5 is 0.86. And we can check that again with the meaning of the log. 5 to the power of 0.86 is about 4. Okay, so we can use a change of base law for part C as well. Log of 6 divided by log of 0.5 is negative 2.58. And we could do a change of base for this one as well. Log of pi to the 5 divided by log of pi is 5. Well, that's interesting. And the reason why is because this means pi to the power of what number equals pi to the power of 5? Well, obviously pi to the power of 5 equals pi to the power of 5. Your ln button is right below the log button. So ln of e is 1. Because ln means log base e. And remember, e is just a number, 2.7 something something. So 2.7 to the power of 1 equals 2.7. Log of 1 means log base e of 1. So it's saying e to the power of what number equals 1? Ln of 1 is 0, because e to the power of 0 is 1. Any number to the power of 0 is 1. Ln of 5 is 1.6. And that's because e to the power of 5 equals 1. Sorry, e to the power of 1.6 equals 5. Let's check that out to verify. E to the power of 1.6 is approximately 5. I need more decimals in order to get exactly there. So to determine this log without using a calculator, I just have to ask myself 3 to the power of what number equals 27? 3 times 3 times 3 is 27, so I need 3 3's. 5 to the power of what number is root 5? Well, I know that root 5 is the same as 5 to the power of a half, so I need my exponent to be 1/2. A to the power of what number equals 1? Well, I know that anytime I raise a power to the power of 0, I get an answer of 1. Now, to write these expressions in exponential form, you can take the logarithm, and the base becomes a base of an exponent on the other side of the equation. So this expression is just saying that 81 is the same as 3 to the power of 4. So the log base 2 becomes a base 2 on the other side of the equation that pushes the negative 2 up into the exponent. 2 to the power of negative 2 is 0.25. So we can take this log base a and move it to the other side of the equation by making it the base of an exponent. If you already have an exponent, you can make it into a log on the other side of the equation by making it a base 5 log. So log base 5 of 125 is 3. So you can take the base and make it a log on the other side of the equation. Log base 2 of 1 over 8, and then exponent will just come down, -3. So to write this in log form, we take the x as a base on the other side of the equation. Log base x of z is equal to y. So your homework for today is to do questions number 1 to 5 from page 167 in the Michelson textbook.